In the previous lectures, we have learned that a fluid is in static condition, or we can just write static fluid, when there's no shearing stresses. Shearing stresses. In other words, if we draw a fluid element right here, the forces that only acts are the normal forces. Right, so also the weight plus the weight. And if that's the case, we have already derived the equation that says that the pressure only varies with depth, and that's the so-called hydrostatic equation, or mathematically expressed as delta P is equal to the unit weight times the change in elevation. Okay, and this holds true for a static fluid. We have also learned that if a fluid is contained in a container and this container undergoes acceleration, then we have learned that this free surface, although this is the initial position of the free surface, and because of the acceleration of the container, this free surface will actually tilt or change its position. And so let's say this is our point 1, and then this will be our point 2. So at time 2, when it undergoes acceleration, then we have this tilting of the free surface. And because of the tilting of the free surface, we have learned that there's going to be an increase in the height. And compare that to the initial position, wherein this free surface is right here, and you have your height, which is lower as compared to the height when you have an acceleration. Okay, and we have discussed that we have to take into account this kind of situations, because we have to design appropriately the thickness of our vessels. Okay, and although this is somehow in motion, in a condition where there's motion involved, although the motion is accounted only for the container, we still use this hydrostatic equation, simply because if we take into if we zoom out one of the infinitesimal element, what we'll see is still a forces that's acting perpendicular to the sides. Okay, so there's still no we'll write it here, there's still no shearing stresses. All right. Okay, so why is that? Because at this particular acceleration, then there's going to be a tilting of the free surface, and once this free surface tilts, then this entire fluid, they actually act as a rigid body. Okay, so there's no motion between the fluid elements. Okay, and that's why the assumption is still, or the method for analysis, that we use these hydrostatic equations, except that we have to take into account the acceleration of the container. Okay, so we can say therefore that the previous topics, they're all about fluid statics. Okay, and right now we are going to delve into fluid dynamics, or fluids in motion. So right here we're now going to start our topics regarding fluid dynamics. So that means that that the fluid itself is in motion, and that means that shear stresses exist, although in some expressions or principles we can neglect these shear stresses or the effect of the viscosity, and we can derive an equation. Okay, so when there's no shear stresses, that just simply means that the viscosity is zero. So in this condition, we can also derive an expression relating the pressure, the elevation, and the velocity of the fluid. Okay, so we will try to derive an expression relating the pressure, the height, and the velocity of the fluid. Okay, so now let's review our kinematic parameters. And these are displacement, velocity, and acceleration. When we say displacement, basically it's just a change in position. So that's, let's say, delta S. And this one, the velocity, is just simply the change of position or the change in position per unit time. Delta S all over delta T. And then this one, the acceleration, is just simply the change of velocity per unit time. So this is V, this is A, and then this is S. And the unit for this one is meters, and this one is meters per second, and this one is meters per second squared. Okay, so for example, we have a path line for a fluid element, and let's say this fluid is traversing this path, and let's say this is our point 1. So after some time, the position change, and let's say the fluid is right here at point 2. So because of the change in the position, then that means that we have a displacement, and how fast does it change its position refers to the velocity, right? So V is just simply the change of position per unit time. And when you say accelerations, it's just simply the change of velocity, which means that, for example, we have this velocity, let's say V1, and then you speed up. So let's say we have V2, and V2 is greater than V1. That just means that your fluid particle is just speeding up. So when you talk about speeding up or slowing down, that's actually the acceleration. Okay, so the change of velocity per unit time. All right. Now, although these are the kinematic parameters, we'll just focus ourselves in this velocity. Okay, so we just want to talk about the velocity, because as I've said earlier, that we want to develop an expression regarding the pressure, the elevation, and then the velocity. Okay, so how do we describe, or how do we characterize the fluid motions or the fluid parameters? Okay, so how do we describe the motion? Okay, so we have actually two approaches for describing the fluid motion. One is called the Lagrangian approach, and the other one is called the Eulerian approach. Okay, so these are the two approaches for describing the fluid motion, and the concept behind this Lagrangian approach is that For example, this is our fluid element. Just draw a cube right here. Okay, so for example, this is our fluid element, and this fluid element is traversing this path. Okay, so this is point 1, and then this is our point 2. Okay, so because we know the path, then we also know, let's say at some point, the velocity. Let's say at point 1, then we can find actually the other parameters. Now, what if we have another fluid element right here? Okay, so in order to describe the motion, then you have to know the path again, another path, right? And now, what if we have a lot of fluid particles? Then of course that's going to be complicated. Okay, and that's why we have this Eulerian approach. Now for the Eulerian approach, let's say we have this flow, this bulk flow of fluid. Let's say we have a lot of elements right here, because we said that a fluid is viewed as a continuum. Okay, and these fluid elements, they have their velocities, right? So they have their velocities or acceleration or position, and the view or the approach of the Eulerian is that instead of tracing the individual fluid particle, instead of tracing the fluid particle, it uses a grid. Okay, so there's a grid right here, and then what it does is it registers the velocity. Let's say at this point, what is the velocity of the fluid that passes at this point at a particular time. Okay, so instead of tracing an individual particle, the Eulerian approach is just actually using a grid. Okay, so it means that in an interval of time, of course, since the fluid is in motion, then at point 1, for example, or at time 1, the fluid that passes right here will be different for, let's say, at time 2 or at time 3. Then another fluid passes at this point again, and then this registers the velocity of the fluid particle. An analogy is that, for example, we have this let's say we have this MRT, right? So it has a lot of passengers, for example, and if we want to know the velocity of this train, then it's like that you are here, you are inside that train. Okay, so that's the Lagrangian approach. Okay, so you are riding in the train, and if you know your distance, then you know your time, then of course you can find the velocity. Now for the Eulerian approach, it is like you are outside the train. So let's say you are here somewhere in a station, for example, and then let's say the train passes by. Okay, so let's say this is the train, for example, and it's like that you are the fixed point in the grid, and at this time, or at time is equal to 1, then you will register the velocity of this train. Of course, maybe using some devices. Okay, so what is the velocity? Okay, so right here in the Lagrangian approach, we use the term path lines. So path lines is defined as a locus of points traversed by one fluid particle over a period of time. And for this Eulerian approach, we use the concept of streamlines. And we define streamlines as a line drawn through the flow field, right, in such a manner that the local velocity vector is tangent to the streamline. Okay, so the streamline is that, I guess we shall draw it like this. Now let's say this is our grid, and let's say the vector is maybe like this, and then like this, okay. So if we want to take the line wherein this this velocity vector is always tangent, let's say it's like this, I don't know how to draw it correctly. I guess maybe like this. Okay, so if we trace these lines where this vector, this velocity vector is always tangent, then that's what we call the streamline. Whereas this one, the path line, actually refers to the path that's being traversed by a fluid particle. Okay. That's right, this is path line. Okay, so now let's move on. Let's talk about the flow classification, or classification of flows. Okay. Actually, there are many ways to describe a flow, except that for now, I just want to limit our discussion to the classification with respect to the kinematic parameters. Okay, so if that's the case, then we can classify the flow as either uniform or non-uniform. Okay, so that's one classification. And the second classification is we can classify the flow as steady or unsteady. Okay, now let's discuss what it means to have a uniform flow or non-uniform flow. Okay, so when we talk about uniformity of flow, we talk about variation of, let's say, properties with respect to space. Okay, this one, when we say steady, or when we talk about steadiness or unsteady, that refers to the variation of properties with respect to time. Okay, so why is that? Simply because, as we always use in mechanics, in the subject of mechanics that we are actually living, matter lives in a three-dimensional space, right? The x, y, and then the z. Okay, so we have space, that's the x, y, z, and then another dimension, which is time, right? So that's why these two are very fundamental for, in the study of mechanics. Okay, so if the properties vary with space, then that's the uniform or non-uniform. Okay, and if we talk about variation of properties with respect to time, then that's going to be the steadiness. Okay, so let's have some example right here regarding the uniform flow, then later on about the steady flow. Okay, so for the uniformity flow, let's consider this pipe, for example. Okay, so this is our conduit, and we will have a flow right here. Right, so we have flow of fluids. Now, if we want to draw the velocity profile, and if we consider a viscous fluid, so when we say viscous fluid, we have to consider the shearing stresses, the existence of the shearing stresses, then the velocity profile would be something like this. Okay, so we have a non-uniform velocity profile. Okay, so again, this is the velocity profile if we have to consider the viscosity. Viscosity is present, or let's say is considered. Okay, so it means that at this, let's say at this point, let's say point A. So at this point, and this is our, let's say this is our x, and then this is our y. Then we see that at this point, let's say the velocity is only up to this point, but along the center line we have the largest velocity. Okay, so in other words, we can say that the flow is actually non-uniform. Okay, so again, this only applies if we consider that viscosity. If we consider the presence of viscosity, but if not, and in many applications also, sometimes we neglect the effects of the viscosity, and therefore, if we neglect that, then of course our profile would be something like this. Okay, so this velocity profile. So by the way, when I say profile, it's actually something like a graph. Okay, so here in this profile, this is called the uniform profile. Okay. So for a uniform profile, so along the y direction, there's no changes in the velocity properties. Okay, so that's the example of non-uniform flow. This one is non-uniform, this is uniform flow. But again, just take into account these conditions. Now for the steadiness of flow, so let's say we will consider again the same pipe, and except that this one is taken at let's say time is equal to 1, or snapshot 1, right? That's or snapshot A. So it's like we are taking a picture with respect to time. Okay, so this one is snapshot A, and then this one is snapshot B. Right? Time is equal to 2, and then this one time is equal to 1. Okay, so if we see that at snapshot A, For example, this is the profile, and then after some time, if we take another snapshot, we see that this profile is or has changed into this profile. Then we can say that this condition is a non-steady condition, right? Because at snapshot A, this is the maximum velocity or the profile, but in this snapshot B, this velocity actually increased. Okay, so if this increased, then it means that the flow is unsteady. So therefore, if we now make a summary of the tables, of this classification of flow, when we say uniform, means that velocity is constant along the streamline. Okay, so V is equal to C, and therefore if velocity is constant, then there is no acceleration. A is equal to 0. For non-uniform velocity changes along the streamline. Okay, and if we write the equation, we have I think I should write it here. So the velocity with respect to the position, this is not okay, and this one will be the change of velocity with respect to position is just actually 0 because it's constant. Okay, and then for the steady, we have this change of velocity with respect to time. Because it's steady, then it doesn't change, then it's just 0. Then this one, the velocity with respect to time for unsteady, it means that it is not equal to 0. Okay, so for the descriptions, we have streamlines pattern are not changing over time. And then this one, streamline patterns are changing over time. Right, so in reality, actually, if we base our flow classification in this according to this 4, then it's actually a combination. So we can have a steady uniform flow. It means that it doesn't change with time, and it also doesn't change with respect to position. Now another one is we can have a steady but a non-uniform flow. So the velocity does not change with time, but it changes with position or with space. Then another one, we can have unsteady uniform, and we can also have unsteady uniform flow. Okay, so now let's talk about the acceleration regarding or related to this discussion. Okay, so we can express acceleration actually as the change of velocity per unit time. So that's acceleration as a function of time, but we can also express acceleration as a function of position, and we have learned that in our dynamic course. So if in terms of position, then we can have A is equal to V dV all over ds. Okay, and if we talk about this acceleration as a function of time, we term this as local acceleration. And if with respect to space, we term this as the convective acceleration. And therefore, the actual equation for the acceleration is acceleration total is just simply the local plus the convective acceleration, and this one is a local acceleration. Okay, so we can take into account, in this expression we can take into account the variation with respect to time, and then the variation with respect to space. However, if we try to separate these two, let's say we have this local acceleration and then this one is convective, and if our flow is steady, uniform flow, then the local acceleration with respect to time, the a dv dt is 0, and we have a uniform flow, meaning it doesn't change with space. The acceleration also doesn't change with respect to space, then this will also be 0. Now for steady non-uniform, with respect to the local acceleration, we have that's constant, that's 0, and then we have here a convective acceleration because that's non-uniform. Now for this unsteady, so we have an acceleration right here, but since it's uniform, then we don't have acceleration in the convective term. And for unsteady, I think this is unsteady non-uniform. This is non-uniform. So for unsteady non-uniform, then we can have both. This one, we can have both accelerations in the local terms and then the convective terms. And therefore, if we want to write the mathematical expression for the acceleration vector, we have this partial derivative of v with respect to x times dx dt plus the partial derivative of v with respect to y times dy dt plus the partial derivative of the velocity with respect to the z-axis, okay, times the dz dt, okay, plus the local acceleration, which is dv all over dt. Okay, so this one is called the convective acceleration, and this one is the local acceleration. Okay, so the equation just simply tells us that the velocity, we have to take into account the velocity along the x-axis, the y-axis, and then along the z-axis. All right, so anyways, we're not going to use this much equations. Again, as I have said, that we're the goal of this discussion is to create an expression relating the pressure, the elevation, and the velocity. So that's why I focused this discussion regarding the velocity. Okay, so in the next video we will start deriving the equations or the expressions relating this pressure, elevation, and then the velocity.